So our function again, y equals x squared minus 2x minus 1 over 3x cubed minus 2x. Now let's take a second and just think about it. As x goes towards infinity, x puts in giant values, 10 million, 20 million, a billion, a trillion. What takes over? What values of this original function is going to take over and define where this function goes? Now, students tend to think in small values. They plug in like 10, and let's plug in 10 here. 10 cubed minus 2 times 10. Okay, what's dominating the function? Well, let's look bigger numbers. If you plugged in 20 million, you've got 3 times 20 million cubed minus 2 times 20 million. Which one has a much bigger impact? Absolutely, that cube, that exponent has huge powers when you take it up to 20 million. Same thing on top. X squared takes over. The x squared value is going to be way more than 2 times x, way more than minus 1. So those largest exponents take over. So what I'm going to show you is the factoring method to find horizontal asymptotes. So what I'm going to do is I'm going to find the largest power of my variable, and I'm going to factor it out. Now, easy question. What's the largest power? X cubed. Let's take it out of the bottom first. So I'm going to factor it out. When I take it out of the bottom, what's left over? Take it out of here, I got a 3. Now, kind of weird, take it out of here. There's 3 I've taken out. There was only 1 to start out with, so I have to have 2 in the denominator. Going up to the top, I'm going to take an x cubed out. When I take an x cubed out, there was only x squared to start out with, so I have to have 1 over x. There was only an x to start out with, so I'm going to have a 2 over x squared. There's only a 1 to start out with, so I'm going to have 1 over x cubed. Now, silly question. Can I cancel this and this? Can I cancel that negative 2 over x squared with that negative 2 over x squared? No, unfortunately you can't. You can only cancel through multiplication and division. So, why do we do that? We now have an x cubed on top that cancels an x cubed because they're through multiplication. Let's look at what's left over. Notice I have a lot of these x's in the denominator. Let's go back to our very original function. Let's take a look at the graph. What happened to 1 over x as x went to infinity? What happened to 1 over x as x went to infinity? As it went closer and closer and closer to infinity, as it went closer and closer and closer, look where it's going. It's going closer and closer to 0. What would 1 over x squared do? 1 over x squared would still go to 0, but even faster. What would 1 over x cubed do? Still go to 0, but even faster. So this great property that as x goes to infinity, 1 over x goes to 0, means for my horizontal asymptote, this goes to 0, this goes to 0, this goes to 0. So on the top I have 0. On the bottom I have 3 minus, what's this going to go to? It goes towards 0. So y equals 0 over 3. So where is my horizontal asymptote after this one? It's at 0. So that's the algebraic way to find it. We have to find that end behavior. There are many ways to do it. The way I showed you here was to factor out that highest power of x. That then takes away everything with that most dominant feature, and then we can see where our function goes as x goes towards infinity. On campus, let's stop and just check up for just a second. Questions on that? Now, again, this might be a spot to stop, do another example. Cornerstone teachers, if you need to. On campus, though, we're going to keep on going. Let's take a look at our last example for this section. Oops. And F5. So, very last thing now, kind of combining everything we talked about with several things we've talked about throughout this section. We want to find the domain, the x and y intercepts, the vertical and the horizontal asymptotes. And if we have a second, we're just going to try to make a rough sketch of that graph. Might be something we leave to teachers on their own time, but let's at least get through that first part, the domain, the x and y intercepts, vertical and horizontal asymptotes of the function. And we have a rational function, top is a polynomial, bottom is a polynomial. All right. The domain, x and y intercepts, vertical and horizontal asymptotes. So first question, let's ask ourselves, the domain. What would prevent a number that we plugged in from giving us a value out? Specifically the fraction. Correct, yes, absolutely. If the denominator is equal to 0. So to find the domain, what members don't work for the domain, we're going to take that bottom, see what values of x we could plug in and get 0 out as an answer. Now, simplify first. What do those two things have in common? They have a 3. What else do they have in common? They have an x. Take that out, what are you left with? An x in the first term. What are you left in the second? The 6. Splitting it up using the zero product property, 3x equals 0, x minus 6 equals 0. So x equals 0, x equals 6. If you plugged in 0, you would not get an answer out. If you plugged in 6, you would not get an answer out. So these are the members of the domain that do not give an answer out. So our first part, the domain, we can go from negative infinity to 0. We can go from 0 to 6. We can go from 6 to infinity. Or another way of writing that, all real numbers except x cannot equal 0, x cannot equal 6. Okay, that's our domain. Second part, we need to find our x-intercept. To remind you again, what is the x-intercept? That's the value you plug in for x to get an answer of 0. So in other words, what number could you plug in and get a 0 off for an answer? Let's take a look. So let's set 0 equal to our function. Now, this looks pretty darn tough. Let's go back to some elementary fraction knowledge, though. If a fraction is equal to 0, is that because its numerator equals 0 or its denominator equals 0? Correct, its numerator needs to equal 0. Now, we do have to be careful. We're just going to set the numerator equal to 0 to find the x-intercept. If that also happens to make the denominator equal to 0, which conveniently we found the two numbers that did that before, that would not be an x-intercept because it would be not part of our domain. So let's take that. 0 is equal to x squared minus 30x minus 10. And let's hope and pray to math that this is factorable. So we have, yep, okay, x minus 5, x plus 2. Again, using the zero product property, our old friend, 0 is equal to x minus 5, 0 is equal to x plus 2. Our two solutions, x is equal to 5, x is equal to negative 2. So those are our two x-intercepts, or where are the points those happen at? This happened at 5, 0, negative 2, 0. Just to double check our bases, is that one of our members that's not in the domain? No, it's not, so those are both good. Next thing, y-intercepts. Now we're going to plug in 0 to see what we get out as a value. So plug in 0, so y is equal to, this is our third part, so we'll call it part C. Y is equal to x, 0 squared minus 3 times 0 minus 10 all over 3 times 0 squared minus 6 times 0. Now, okay, I see the look on campus, but let's do the work here. Let's go through this. 0 squared is 0, minus 3 times 0 is 0, minus 10 gives you negative 10 on top. 3 times 0 gives you 0, 6 times 0 is 0, negative 10 over 0, which gives you an undefined, or no solution. Now, how could you have known that without having to do the work for this particular problem? It's because 0 is not a member of the domain. Therefore, there are no y-intercepts. In other words, there's not a number you could plug in at x equals 0 and get the solution out. Okay, part D. We've already done the work for this, the vertical asymptotes. Where what number can we plug in and not get an answer out? Those were at x equals 0 and x equals positive 6. Last part, the horizontal asymptotes, as we just talked about. This one we're going to have to write that original function out. Y is equal to x squared minus 3x minus 10 over 3x squared minus 6x. Okay, what's our largest power? It's x squared. Let's factor out x squared, both the top and the bottom. Again, if you want to verify, if your life depends on it, multiply that x squared out. Should get your original function back. Again, why are we doing this? The power is what takes over as you plug in giant numbers as x goes towards infinity. So that's what takes this function over. So the x squareds cancel out. What happens to the top as x goes to infinity? The 1 just still stays a 1. This goes to 0. This goes to 0. On the bottom, the 3 stays put. 6 over x goes to 0. So we're left with a 1 on top, a 3 on bottom. So our horizontal asymptote for this, or in other words, as x gets giant, where's our y value approaching? Both as you go to positive infinity and negative infinity, it's approaching y equals 1/3. Now, the temptation in this particular section is to use the graphing calculator to find all the answers and skipping all the algebra. Well, the graph is a great way to check your answer, but you still have to be able to algebraically verify your solution. So we are going to take a look at the graph, but I caution you in this. Don't just plug these functions into your calculator, see what they are. Okay, there's an asymptote between 1 and 0, so let's call it 1/2. Still have to be able to find the solution. The analogy I use is, like planes right now are high powered by computers. But if those computers go out, you still hope the pilot could land the plane, that he could do the math to figure out where he needs to land. So most of the time you are going to use technology to help you find these solutions, but you still need to be able to find them out. So let's take a look at our graph. And conveniently, there's our function. And let's plug in our lines. We had a asymptote at x equals 0. Oops, and I got a circle instead of a line. We also had an asymptote at x equals 2. We had a horizontal asymptote at x equals 1/3. So this one I will have to approximate. That's about half, so let's go there. There. All right. Okay, that's 4-7. Again, that's the end of chapter 4. We'll talk again on 5-1 next week. Thanks.